Patients manage to ingest or insert an iPod, a gun, even dolls have shown up on x-rays, and now a picture book of wayward x-rayed items has been published by a trio of physicians. CNN's Jeannie Mose gets to the bottom of things.
Did we say that this goes here and not in here? An electrical cord x-rayed in somebody's gut? And there are 100 of these. What was the gun doing up there?
Well, with the tuna can lid.
The tweezers. What could they have been trying to pluck? The x-rays are all in a new book called Stuck Up. 100 objects inserted and ingested in places they shouldn't be. It's co-authored by this emergency room physician and 2 other doctors. We doubt the patient's going to be able to pass the soap, or the peppermill, or the egg beater, or the chopsticks.
Most commonly, we do see long, slender objects, because that is the most form-fitting.
We're not going to dwell on how these everyday objects ended up where the sun don't shine. Most of the time, it was not an accident, though often that's what people claimed.
I accidentally fell on an object. That's probably the most common accidental story you'll hear.
And who hasn't sat on their glasses really, really hard while nude? The doctors say the x-rays are real, though outlines of some objects are graphically enhanced so the reader can easily see them. Everything from a computer mouse to a cassette tape.
That was definitely an older x-ray.
A more recent x-ray displays an iPod Nano. We can only imagine its playlist. So how did that gun get stuck in the middle?
That's just dangerous.
Certain people love their guns.
The good news,
It was not loaded.
though maybe the patient was, and you thought a light bulb went off in your head. How about this light bulb in someone's gut? And this string of Christmas lights? The series Scrubs did a whole episode on the subject.
This kid has a light bulb up his butt or his colon has a great idea.
Scrubs accurately describe how to remove a light bulb.
All you need to do is thread an angioplasty balloon past the bulb, inflate it, and then pull forward.
One of the oddest items? See? Where that tuna lid rolled up like a cigar ended up. But the doctor's favorite found objects are action
Buzz Lightyear.
figures for Buzz Lightyear from Toy Story.
To infinity and beyond.
He said beyond, not behind. And this is Barbie, but it isn't her dream house she's in. Jeannie Mose, CNN.
Hey, do you have a magazine?
Not in me. I mean, on me.
New York. I'm just shocked. How?
It's a very common thing when you work in a hospital. You see a lot of objects, especially gel tape. A lot of inmates like to swallow razors for some reason. When I work with them, I have to do an abdomen X-ray to see where the razor goes through the body. Partly because they want to get out of the hospital, out of jail, so it could be in the hospital. Different scenario. So
Whatever motivates you.
all right, X-ray production. So this is 1 to 7 of it. In order to generate X-ray, we need to have 3 things happen at once. We need a source of electrons, and that is where the cathode provides the electrons through the process of thermionic emission. And those electrons have to escape at a very high speed, so they have to accelerate from the cathode to the anode within an inch apart at a very fast velocity. In fact, they travel almost at the speed of light. And then when it goes through the from cathode to the anode, it has to hit a target. So that's where the tungsten disk comes into play. The interaction between the thermal emission electrons and the electrons atoms of the tungsten disk, fast-paced collision then produces X-ray photons that emit out from the tube. In the process of producing X-rays, 2 things can occur. We have the primary beams on one side, and then after the primary beam interact with the object, it then produces scatter radiations. The interaction between the X-ray tube, between the filament electrons and the anode target atoms. So the filament electrons, the process of thermal emissions, and the tungsten disk, the electrons interact with the atoms of the tungsten disk. In this process, it produces two useful diagnostic X-ray beams. One refers Branson log X-ray radiations, and the other is called characteristics X-ray radiations. So those are two primary beams, useful primary beams coming out from the tube. Once these beams interact with the patient or whatever, it then produces scatter or secondary radiations. And there's 5 types of scatter secondary radiation that you need to know. Classical, Compton for electric, head production, and for disintegration, ranging from the lowest, from the weakest energy to the highest energy level. We're going to discuss more of this next week. Today we're going to discuss mainly about Branson radiation and characteristic radiation. Yes?
What are those 5 types of radiation going
Those are scatter secondary radiation. Remember the first day we talked about scatter secondary? So these are the different types of scatters. Everyone have this down?
No.
Oh, okay.
I didn't realize we were supposed to print out something.
Oh. You done?
Yeah.
Okay. With the interactions from electrons and the target disk, 3 things occur. I mentioned for production of Branson-like radiation, very known just Brams radiation, and Catcher's radiation. It also generates a lot of heat during the productions of X-ray. In fact, the production of X-ray is very, very inefficient. A vast majority of those electron interactions will convert into heat, or why very select few actually becomes X-rays, photons. So we can talk about heat production. Electrons that travel from cathode to anode, 1 to 3 centimeters, which is about less than an inch or so, travel close to the speed of light, half the speed of light. Those through the process of thermal emissions, these electrons refer as projectile electrons. So it's projectile from the cathode to anode, very, very high speed. Some of these projectile electrons, will convert into X-ray photons, while a vast majority will just interact with the atoms of the tungsten disk and become heat. In fact, 99% of the kinetic energy of the projectile electrons is converted to heat. Only about 1% of those thermal emissions actually convert into X-ray photons. So it's very inefficient on average. To increase the efficiency of X-ray productions, the higher the kV, kilovolt, the energy level, the higher the efficiency of X-ray productions. So when talking about like in the radiation therapy, it's the megavolts. So it generates more than 1%. I can't remember exactly. I think it's like 5% of the X-rays of the mega electron volts compared to actually to X-rays. So it's very, very inefficient. If you can find a better way to produce X-ray, you could become a millionaire. Or a billionaire. So the higher the kV, the more efficiency X-ray production is occurring. Okay, heat units. Different type of generator will generate different type of heat units. And this just measure a heat unit is not temperature scale. So it's used on anode cooling charts to determine how long it takes to cool off the X-ray tube. With a single phase generator, the basic formula to calculate the heat units will be just the techniques and then the number of exposures. So the following will be kV times MA times seconds, or just kV and mass if it's combined, plus times the number of exposures. With three-phase, 6 poles, everything the same, with section included 1.35 constant number. Three-phase 12 poles, everything the same as single phase. The difference is you have 2 times with a constant number of 1.41. And then we have high frequency generator. They're the same, with the exception that you use a constant number of 1.45 as the constant number to calculate the heat unit. So let's do an example. How many heat unit will be generated in a tube with the following exposure factors from a single phase generator? Here's the following technique: 75 kV, 100 MA, half a second, 3 exposures. Since it's a single phase, I will just multiply across the row with the technique and exposure. So 75 times 100 times 0.5 times 3. Times 100. So the heat unit from this will be 11,340. Heat unit. Pretty difficult. Any questions? Let's do a different example. What is the heat unit from a single exposure at 100 MA, 60 kV, 5 milliseconds, at a distance of 120 centimeters using 3-phase 12-pole generator? Three-phase 12 poles, what is the constant number?
1.41.
1.41. So we're going to multiply 60 times 100 times 5 milliseconds. Move decimal over. 1, 2, 3, so it'll be 0.005. Times 1.41. How many exposure?
1.
1, so we don't need to write that one. Let's multiply. 60.
It says 5 milliseconds. Yeah.
42 from this one single exposure based on the bond technique.
That's it.
Thanks. Any questions? very straightforward. Just calculate the techniques and then number exposure and what type of generator is being used. All right, let's do one last example. How many heat unit will be generated in a three-phase exposed unit using the following exposure factors? We have 70 kV, 100 MA, and 500 milliseconds. It didn't specify how many exposure we have, so I'm just assuming it's going to be just one exposure. With a three-phase exposed, the constant number we can use will be
1.35.
1.35. 70 times 100 times, wait a second, 123.5 times 1.35. What's like that? 70 times 100. 47.25, that's correct?
Mm-hmm.
Based on this number, when you actually look at the chart, the annual cooling chart, it's like a decency scale. There's a timing, you just determine heat unit, and then you just determine how long it takes for it to cool off. So that's how we get the heat unit and calculate for heat units. Now, the other part of the interaction would be the production of Bremsen-Log radiation, or just known as Bremse radiation. It's a German word meaning to break or slow down. The process of producing this type of radiation occurs when the electrons, those projected electrons, come very close to the atom of the tungsten. As it gets close to the nucleus of the tungsten atom, it slows down. The slowing down process then releases energy in the form of X-ray photons. So that's why we call it Bremsen-Log radiation, because it comes very close to the nucleus of the atom of the tungsten, and then the slowing down releases the energy in the form of X-ray photons. With the productions of Bremse X-ray radiations, there's no ionizations occur. It doesn't kick off an electron from the tungsten jets. It doesn't mean that Bremse radiation is not ionized. It's just the production of this type of X-ray have no ionizations in the process. Bremse radiation constitutes a vast majority of the X-ray used for diagnostic X-ray coming out from the tube. It's accountable 80 to 90% of the radiations coming out from the X-ray tube. Now, as you increase the level of kV or energy strength of the technique, Bremse radiation will also increase in both quantity and quality, both the number of X-ray and the strength of X-ray. And on the average, Bremse radiation is about 1/3 of the average. Remember on the first day of first lecture, I mentioned one of the property of X-ray is polyenergetic. I mean, it ranges from whatever technique you set, from 0 to your technique. And if you call it, say for example, it's 90 kV, your technique, so it ranges from 0 to 90. And on the average, it's about 1/3. So if 90 kV, what's the average of 90?
30.
So 30 kV. So on average. Any questions with Bremse radiation? This is a drawing of how it works. The projected electrons come from the cathode, going to the atoms of the tungsten disk, get close to the nucleus. As they get close to the nucleus, it slows down. And then when it slows down, it releases energy in the form of X-ray radiation, and we call it Graham's radiation due to the process. And then the projected electron moves out of the way. No ionizations occur in this process. The other type of radiation coming off from two, actually here's an animation. Would be characteristic radiation. This constitutes account about 10 to 20% of the X-ray productions, depending on the level of energy. Characteristic radiations produced occur when the filament electrons, those projected electrons, interact with the shell level. And when it interacts with shell level, it would then knock those electrons out. When the electron got knocked out, it wants to fill in that hole. So the next shell level, whatever shell level, will move in, and replace that missing electrons. As one electron from one shell level moves to the next shell level, it then releases energy. And this energy is referred as characteristic radiations. And we name characteristic radiation based on what hole or what gap the shell level is filling in. If, let's say for example, an electron is knocked out at the K shell level, remember K is the first shell, and then the electrons from a different level move in, filling that K shell hole, we refer as K characteristics, X-ray radiation. If L shell electrons are removed and a different shell move in to replace that gap, then we refer as L shell electrons. So whatever the electrons missing and moving into fill that will be referred based on the shell level. And in diagnostic X-ray, only K characteristic X-ray is useful. Every other type of characteristic radiations is useless. It doesn't account for diagnostic X-ray. The patient just absorbs that.
So is it considered scatter radiation?
No, it's just weak energy.
Okay.
Because these are the primary beam characteristic and abundant radiation that's coming out from the X-ray tube refers as primary beam. After it interacts with the patient or the object, it then refers as scatter radiation.
And you're saying X-ray energy is emitted through the process of that electron moving from one shell to the other?
Yep. And then we name the characteristic based on whatever shell is going in. The energy of the characteristic radiation is based on the differences of the binding energy that it's moving from one shell moving into the other shell. So where the binding energy is. For example, K characteristic of tungsten disk have an energy binding of, at K level, 69 kV. And let's say the next shell, it doesn't have to be the next shell, it could be any shell that moves in to cover the gap. And if the one electron moves out, L shell have a binding energy of 12. The difference between 69 and 12 57 kV. So that's the energy strength of the K characteristic. As the atomic number increases of the material, characteristic radiation will also increases. So it's based on different bindings. In order for it to have useful diagnostic X-rays, the energies have to be 69 kV. The projected electrons have to be strong enough, have to be at least 69 in order to knock the K binding energy from the tungsten disk. If it's weaker than that, it won't knock down the K binding energy. It will knock down other binding energies, maybe such as L, M, but won't knock down K. And those L, M, and so forth will be just useless X-rays. Not useless, it just won't account as part of the diagnostic X-ray. The only thing that's useful is the K characteristics X-rays. Anything below that, just absorb, the patient absorb. And when you increase in the energy of the X-ray, when energy increases, what happens to frequency again?
Increases.
Increases and wavelength decreases, right? So with K characteristics, ionizations, the process of ionization occur in this type of X-ray productions.
Because it's knocking out the electron.
Because it's knocking out electrons from the tungsten dust. Not the electrons, or multiple electrons. So those are two prime differences in terms of how X-ray are produced, and those are the two that's coming out from the beam, from the tube. Animation. Okay, so project electron knock out K shell, and then any shell level will move in from the gap. As it moves in, it releases an X-ray photon.
Only on the K shell.
Hmm?
It has to be the K shell.
It has to be K shell. I mean, it could knock out other shell.
But for it to be productive, right?
It won't be used for diagnostic X-ray. The only useful diagnostic X-rays in characteristic X-ray will be K characteristic X-ray, then after K shell. Other type of characteristic X-ray, L characteristic, M characteristics, N characteristics, would not be used for diagnostic X-rays.
So it's just by chance which one it hits?
Yeah. Any other questions? So I mean, in theory, there's multiple type of characteristics coming out, but only K characteristics. Okay, so here's a graph of the spectrum, X-ray spectrum. That's the X-ray energy coming out from the tube, and based on the number of X-ray versus the X-ray energy. And since it's polyenergetic, it ranges from 0 kV coming out from tube all the way to whatever the setting is. And at the point 69, that's where the energy level needed for K characteristics produced, you see a spike right here, and then go down there. X-ray emission spectrum. X-ray emission spectrum is pretty much a graph that represents the amount of X-rays coming out from the tube. And we base this on the number of X-ray versus the energy of the X-ray. So quantity and quality. Pretty much like what it is, quantity and quality. Number of X-rays is the quantity, X-ray energy is the quality of the X-ray. And then the graph, almost like a bell-shaped curve.